So we left off after a whole bunch of different alloying things, and the question of zirconium came up, and it turns out in superalloys, zirconium is not as strong of an oxide former as I thought, and I don't exactly know why, right? But pure zirconium, right, at high temperatures, the formation of zirconia is very favorable and highly exothermic and causes nuclear power plants to explode, like in Fukushima. So I have to do a little digging. My chemical metallurgy is a little weak on that particular area. But zirconium is not as strong of an oxide former in superalloys as I had thought. It's generally also doesn't contribute very much to the formation of carbides, which is also confusing, being that titanium and hafnium, which are also group 4 hexagonal metals, are very potent carbide formers in here as well. So I need to wait for Professor Mills to get back from MRS and ask him what the deal is with zirconium and in superalloys. But we do know that it does segregate 2 grain boundaries and is important for additional creep strength because it lowers the grain boundary energy. Carbides are also very important for high temperature creep strength. Right, so there's added carbon at very small percent where they'll combine with the refractory elements and form these blocky carbides on the grain boundaries, right, that during service and heat treatment, they'll form lower carbides such as the M23C6 and M6C, which form on the grain boundaries, right? And these are all based on the FCC crystal structure, right? So they are can be fairly coherent. They are beneficial at high temperatures because they lead to the formation of these serrated grain boundaries, right? Which are very favorable for creep, right? Because at high temperatures, grain boundary sliding and grain rotation are critically important creep rate controlling mechanisms, right? So if you have a tortuous grain boundary like this, you do not have nearly the ease of grain boundary sliding. Okay, so in the gamma matrix itself, we are primarily adding alloys for solid solution strengthening, right? And this basically just shows you for different elements a schematic of the increment in yield strength due to them being in solid solution, right? And there's some empirical relationships that you can use to determine the effect of strengthening as a function of the alloy composition, right? And if we remember back to the very beginning, we know we have 2 main effects for solid solution strengthening, right? We have a lattice mismatch, lattice size effect, and we also have a modulus effect. And we can look at the change in lattice parameter for all the different elements. And we notice something really interesting here. If we look at aluminum, it is predicted to have the largest effect when you take the modulus effects into account as well, right? So in principle, aluminum would be a great solid solution strengthener for the gamma phase. The only problem is, where does it go? It partitions to the gamma prime, right? So even though it's there and very potent, it is really added for its H hardening purposes rather than its use in strengthening the gamma phase, right? So that means the tungsten, molybdenum, and chromium are primary solid solution strengtheners to the gamma phase. Iron iron titanium. Right? I saw TiCO and combined it together. Iron, titanium, cobalt, and vanadium only contribute in a lesser way. Right? And this solid solution strengthening is going to persist to about 0.6 of the melting temperature, about 815 C. After that, we have just too much thermal activation, right? And it's easy to get around, right? There's not a whole lot of interaction between the dislocations and the solid solution strengthening anymore. Yeah.
The previous page, titanium is not so high, but titanium for low stress, changing low stress.
Yeah.
Yeah.
Yeah. So titanium's fairly low here.
Yeah, but
it has a relatively small change in the lattice parameter, and the modulus is not significantly.
It is one of the primary strengthener for gamma phase. Yeah.
It contributes less. It's a stabilizer for the gamma phase. It's not necessarily a strengthener for it, right? Right. And then, back. Yes.
How do you measure the strengthening for just the solid solution? In the alloy, you also have the
gamma prime.
And then the solid is also affecting the strength of that, and then there's also the anomalous gradient.
Yeah, so the gamma prime, you can measure the yield strength. You can correlate very well with hardness, right? So historically, it was done by Vickers indentation. Now it's done by nano indentation. But you can correlate very well the relationship between yield strength and indentation strength, right? So you can be between the gamma prime particles, right? And generally, these measurements aren't done on on blade alloys where you have 80% gamma prime, right? These will be done on lower strength, lower gamma prime fraction alloys. Right. Once we get above 0.6, we have diffusion to consider, as well as the thermal activation of dislocations, right? And so our strengthening is in some ways going to be limited by the diffusion of our alloying elements, and so slow diffusers like molybdenum and tungsten are critical, right? And we also have to consider cross effects, right? So these heavy refractories also slow the diffusion of titanium and chromium at even higher temperatures, right? So this strengthening in the gamma phase is relatively simple to think about at low temperatures, but under in-service temperatures, it becomes quite complicated, right? You have easy dislocation motion, relatively fast diffusion, right? So you have these refractories in there because they essentially keep the solid solution, this strengthening elements from catching up with dislocation motion, right? Preventing dynamic strain aging type effects. In gamma prime, to a first assumption, we just think of it as we would any other precipitate, right? And so that means the strengthening effect for a given volume fraction of gamma prime is going to depend on the particle size, right? And this mirrors what we saw before, right? So you can think of this as being analogous to the cutting and looping curves, right? So that as we make the particles larger, they become more difficult to cut, but eventually for a given volume fraction, they become too far apart and it starts to become easier to loop, right? So something interesting happens. So here we have, if we look at the flow stress as a function of the fraction of gamma prime, right? So we see our behavior that we expect, but for relatively high gamma prime fractions, the strength increases with temperature, right? And these curves are offset by temperature. So what the heck is going on here, right? And really this is the anomalous strengthening, right? And so if we look for a constant specific microstructure, when we look at superalloys, we see this increase in strength as temperature increases out to about 600 or 700 or so, depending on the alloy. New alloys, this peak can be out around 800. But then we see a drop. Compare that to what we expect from thermal activation of dislocations. We expect to see a very precipitous drop of strength, right? Something along the lines of this. So what on earth could possibly be causing this this behavior? Well, nickel superalloys are like any other, right? We primarily are relying on dislocation motion for plasticity. So we can start there, right? So in FCC, we have a 1/2-110 dislocation. So this is still in the gamma here, right? These are usually going to dissociate into two Shockley partials of type 16211, right? Separated by a stacking fault between the two. So if we look at what happens in the gamma prime, a full 1/2-110 atom, right? Our full 1/2-110 dislocation is going to move the nickel atom to move onto the aluminum sublattice and the aluminum atom to move onto the nickel sublattice. So a full FCC dislocation is a super partial in the gamma prime, the L12 structure, and its passing leaves behind a antiphase boundary, right, where we have mismatch. So we need two full 1/2-110 type dislocations to bring it back into correspondence, right? So full dislocation of type 110, right? Generally, we have 1/2 110s that are full FCC dislocations, partials in the L12 with a antiphase boundary separating them. All right? So each of these superpartials, though, are also can dissociate into a pair of Shockley-like partials, right? But instead of producing an intrinsic stacking fault like it would in the gamma, we have a change in the local chemical environment, so we produce a complex stacking fault. So generally what we have in the gamma prime, right? So first we have a Shockley partial from the gamma, right? It's going to leave behind a complex stacking fault. Another one comes by, leaves behind an antiphase boundary. Another one comes, leaves behind another complex stacking fault. Another one comes and restores us to normal order, right? And of course, these faults all have different energy, right? So the separation of these partials is going to be dependent on the energy, right? So these complex stacking faults are higher in energy. They're going to be much narrower. These Shockley partials are going to be much closer to each other than the ones that create the antiphase boundary, right? Roughly about 10 times as long, right? And here we can see these are the Shockley partials, right? At the this is the gamma prime interface. These are wrapped around. The geometry is difficult to get your head around when you first start thinking about these things. But we have loops of partials in the gamma that wrap around the gamma prime particles. Okay, so this explains why gamma prime is such a good strengthener, but it still doesn't explain the anomalous hardening, right? So we're working towards that. So we know that the yield stress of the gamma prime increases with temperature. So what dislocation mechanisms do we have available to us that also increase with temperature, right? And so Kuhr and Wilsdorf came up with this idea, and they said cross-slip seems to fit the bill, right? It's going to increase, the ease of cross-slip goes up as temperature is increased, right? But the question is, cross-slip from what onto what? So they claim that these partials are going to be cross-slipping from the 111 plane, where they typically want to reside, onto a cube plane, onto the 001 plane, right? So why on earth would this happen? They made some estimates and said that the antiphase boundary energy is much higher on the 111 planes than on the 100 planes. So you've got these partials that are separated. They have a antiphase boundary. If they change planes, they can reduce that fault energy quite a bit, right? So basically, the picture looks like this. We have two partials on the 111. They both cross-slip onto the 001 plane, and now they're spaced farther apart because this boundary energy is lower. They can be farther apart and still reduce the energy, okay? And so essentially, they can't glide on the cube plane, right? They're sessile. So these dislocations are now locked, right? The only way we can get them to move is to increase the applied stress, right? Therefore, strengthen it, right? Okay. Okay. So now what happens once we get above the peak we now have enough thermal activation, to reduce the chiral stress, and are able to move these dislocations and permitting them to glide primarily by cross-slipping back onto the, cross-slip back onto the 111 planes, right? So that's the idea. It turns out it doesn't work nearly that nicely, right? But so people did a lot of experimental work and showed that the antiphase boundary energy on 111 isn't that much greater than on 100. And Kieran Wilsdorf, they essentially did all their calculations considering only isotropic dislocation interactions. If you actually take the anisotropy of the gamma prime phase into account, the interactions become a lot more complicated. The mathematics become much more difficult. But what the folks behind the PPV model did is they essentially did that, and they came up with calculations that show that the strain energy of the superpartials becomes lower when the dislocation is on the 001 rather than the 111. So it's not the antiphase boundary energy, but the elastic energy due to the neighborhood distortions caused by the core of the dislocation, right? So this reduction of energy actually gives you a torque acting on the dislocation, a twisting moment acting on the dislocation, which then encourages the cross-slip, right? So it's a much more complicated picture, but generally it can be, the details behind it are more complicated, but the big story is basically the same. At elevated temperatures, the cross-slip becomes easier, and there's an energetic driving force to drive them onto cube planes where they're sessile rather than the 111 planes where the dislocations are mobile, right? Yeah.
This picture, how do they explain the reduction of the, can explain the increase, so why it doesn't?
It's just a thermal activation argument. Essentially, you get enough that you have enough motion that you reduce the chiral stress, and once they start moving, they cross-slip back onto 111. I don't have a really good, solid answer, right? This is just, right? I don't know if anyone's actually really done the atomistic simulations, right? It's not an easy simulation to do, right? There are reports of it, right? But you have to look at it at high temperatures, right? So it's not an easy thing, right? This is still very much kind of open, I would say, right? I don't think this is settled. The basic ideas are there, right? That we have a cross-slip mediated lock that forms, but the details of it are still, right? The number of right, the number of phenomena that we've mentioned that we don't have a really 100% clear picture of is probably more than the ones that I said that we do, right? right? So, you know, I have a couple bullet points here that talks about constriction and thermal energy, right? You have displacements that are out of the out of the slip plane, but this is still a very hand waving argument, right? And so take it with definitely a bit of a grain of salt. Right? So we can look at this as a function of gamma prime fraction, right? So pure nickel 3 aluminum, pure gamma prime, right? You can see the huge increase in flow stress with temperature, whereas pure gamma definitely decreases. And if we look at about 80% gamma prime, which is our single crystal blade alloys, right, we have a huge increase in strength up to temperatures exceeding 800 C, and then they start to go down, right? Now, what's our turbine temperatures that we talked about before, right? We were talking about turbine inlet temperatures of 1400 to 1500 C, right? So we don't have this increase in strength anymore. It falls, right? But the fact that it's still stronger than any other alloy, right? So don't get confused, because people did this, a lot of people wrote this last year on the exam, that the superalloy retains all of its strength at high temperatures. That's definitely not true, right? There is a clear drop in strength with increase of temperature. It just retains a larger fraction of its strength at high temperatures than other alloys, right? You can't get around the thermodynamics, right, of the situation. Yeah.
I have a small question. I was just wondering that when you have 10% versus 2% are you changing it by changing the alloy composition? There's a lot of, in literature there are reports of some alloy elements kind of changing the anomalous strength behavior. I don't understand how is that. The second question that I have is again, in these volume fractions of exhibits, they might just be like one mole distribution, not just be like
Yeah, no, you're exactly right. It's just washing away all the details of the microstructure, right? What
I'm just concerned how accurate this is.
yeah, I wouldn't be at all quantitative on this, right? This chart, this is an old chart. I believe it's out of, since this isn't my slide, I don't know the exact the exact reference for it. But this is not all the same exact composition, right? And so what difference the initial strength is as a function of composition versus a function of gamma prime fraction, right? You can't necessarily deconvolve those, right? And also the alloying elements will have a significant effect on the anomalous, the strength, the effect of the strengthening, because of where you still have the solid solution strengthening effects in the gamma prime as well, right? Depending on where the gamma prime partitioning elements are they on the nickel aluminum sublattice, how sensitive they are, right? Some alloying elements don't care which sublattice they're on. Others have very strong preferences. And so the specific composition of the gamma prime is also going to affect the anomalous strengthening as well, right? But trends, right? I like trends, right? So nice, pretty big picture kind of stuff. Okay, so as we, the question was perfect because it was a great lead-in, because the composition also is going to affect the APB energy and fault energy, right? Certain alloying elements might reduce these fault energies, others might increase the fault energies, right? The gamma prime strength is also a function of the composition. The diffusion at elevated temperatures, right? Do I have heavy refractories in there or not? The coherency strains are going to be a direct function of the composition, right? How right? The modulus mismatch and the phase fractions, right? These are all explicit functions of the composition, right? So it was a perfect example, right? So this is just the APB and fault energies, right? This was the same picture that we had before, okay? So we do, right, even though we have a perfect order that is reestablished after the passing of two same-signed 1-1-0, 1/2-1-1-0 dislocations, right, we still get really significant strengthening, right? We talked some of the reasons why the particles are different to cut, but a single dislocation is going to come in, right? And by entering the gamma prime phase, it increases the energy quite a lot, right? So that means if we had perfect 1/2-1-1-0s, which we don't, we have Shockley partials, but just imagine that we have 1/2-1-1-0s, the first one's going to come up, and it's basically just going to hang out there at the interface, right? It's not going to cut in because the energy cost to create an APB is too high, right? So essentially, it's going to wait till a second dislocation, same sign comes up, right? But they're the same sign, so they're repulsing, right? So you have to bring them close enough together for them then to cut so that the width of your APB interface is small, right? The same thing, the same types of reactions have an even more complicated when you take partials into account, right? A lot of the mechanisms involve local reordering, right, to reduce fault energy, right? So you have to have partials of the right type, Shockley partials of the right type, either on the same plane or separated by one lattice plane, right? So there's a significant chance and time effect to get the right dislocations to cut through the gamma prime particles, right? Because otherwise the energy cost is just too hard, right? We also have solid solution strengthening of the gamma, right? Right? It's not as strong. Oh, I'm looking at the wrong table. This is the max sort of atomic percent that you can put in here, right? Titanium is quite a strong solid solution strengthener, right? Chromium is an interesting one because it's a strengthener at room temperature, but at elevated temperature, it leads to a weaker gamma prime, right? But titanium, niobium, and tantalum are the major solid solution strengthening phase. Okay? During creep, right? We have to take diffusional mediated mechanisms into account, right? So again, the heavy, slower diffusing high melting point refractory metals are very good for providing additional strength in the gamma climb, right? And then we also have to consider the effect of the coherency strain, which will, right? So if we look at Vickers hardness as a function of modulus mismatch, right? So this is, if we put in alloying elements, I don't have a title, a bullet point for this. Right, well anyway, if you have a mismatch of the percent between, modulus mismatch between the gamma and gamma prime, you're also going to have the same effect. Somehow when revising these, I deleted the bullet point there. So make a note, right, that we have to consider the gamma prime modulus counteracting purposes, right? So sometimes you might want to add an alloying element to increase carbide formation, but then it's going to decrease your coherency strains, right? So everything has to be taken sort of together, right? There's a lot of trial and error optimization that goes into these. Okay, so we're going to wrap this up Friday, and with some pretty sort of qualitative description of stuff and looking at lots of pretty micrographs. Okay, so we will see you then.
So the last thing that we have in the exam,
What's that?
because it's the last part in the exam.
Yeah, so the magnesium and the other stuff were just for information. It's not going to be on the exam. Oh, these lectures will both be put up tonight.
Yeah.
Yeah.
Recorded lecture. Yeah.
The recorded ones, yeah.
So